So thanks everybody. I'm Luke Thomas. I'm the Chief Design Engineer for Product Security at Rolls-Royce. Jet engines, not cars. No, I don't get a car, unfortunately. And I'm going to take about 30 or 40 minutes and talk to you guys about some insights that we've had about how we secure cyber-physical systems and what it means. And in particular, I'm going to really try and take and focus on how our mentality and how we think drives those changes. So let's start with a question. And this is an audience participation moment, so I want to see hands. Who here has an internet-connected device in their home? Yeah, okay. Now look around. No, hold on. Keep them up. Look around. Okay. Keep them up. Who here has an internet-connected device in their bathroom? I do, actually. A few of us do. Who here has an internet-connected camera in their bathroom? Exactly. Why? Why? Right? That's a very visceral reaction, but it's the right one. Would it even matter if I told you what software was in it? No. All right, hold that thought. We're going to come back to it. But we got to start somewhere else. And so let's start with this. What are we watching? It's a video game. Anybody recognize what video game it probably is? A rip-off of Doom. There we go. Now, looking around the room, I'm guessing a few of us have played Doom, but maybe not everybody has. But this, I think, is actually really interesting. Because this, wait just a moment. Does anybody can tell what they're doing? They're farming? They're driving. Now, I live in Indiana, so we're driving a tractor in Doom. Right. So this is actually a port of Doom. And if you look, I zoomed out, and you look at the very top. Anybody recognize what it says? John Deere. So this is actually a video game running on a tractor. Now this was about 3 or 4 years ago. It was a demo given at DEF CON, where a researcher had figured out how to attack the computer in the John Deere tractor and run Doom on it. And the point of this was it was fun, but he was also demonstrating what a lot of people want to do, which is they want to take and modify their physical systems, the computers in them. And there's actually a huge market for farmers to be able to go and modify their tractors because they think, I bought this thing, why can I not modify it? And interestingly, I'm going to assert that Doom on a tractor was inevitable. Inevitable. And I mean that seriously. It was inevitable, but why? Well, okay, looking around the room, my guess is most of us know what Doom is, but I'm going to give you an intro if you're not familiar. Doom was a game back in 1993. It was to your point, it was a first-person shooter, and you got to play as the eponymous Doom guy. I don't know what he was, but he ran around and he blew up demons. It was a fun game, and actually it was really pioneering because it pioneered a whole bunch of really interesting stuff with regard to online video games, first-person shooters. Online distribution, 3D graphics, networked play, all sorts of stuff. It was really, really influential at the time. And since then, there's been this kind of ongoing game that's happened that wasn't part of John Carmack's original vision for Doom, where people have taken Doom and they've tried to get it to run on all sorts of things that it was never intended to run on. There's a whole Reddit called Will It Run Doom? And they've run Doom on an increasingly ridiculous number of things. And I'm going to show you a few in my personal perspective of increasing ridiculousness. And I think the core idea here, so this is actually the sick codes, the hacker in DEF CON who actually showed how to run this on a tractor. Curious people have ported Doom to all sorts of systems. So let's start with one that feels fairly benign, a printer. So in this case, it was I'm not sure what printer it was, but they ran Doom on it. Now the colors are a little bit messed up, but I showed you what Doom, the beginning of Doom looks like, and you can clearly tell what they're doing. Pretty cool. All right, let's go slightly more ridiculous. And for this audience, maybe a little retro. I'm more of a HP kind of guy than a TI, but you get the idea. Here we have a TI-83, and we're running Doom on it. Also, pretty wild. And now, if I was to ask you what's the most ridiculous thing you could think we ran Doom on, anybody want to make a guess? Dishwasher? It's a great guess, but nope, not what I'm going to show. Go. Sure, lots of computers. A missile? That would be disturbing, but no, that's not what I'm going to show you. Instead, this is a pregnancy test. So now, this is, again, black and white screen, but you can clearly tell they're running Doom on a pregnancy test. Now, full disclosure, there were a few licenses taken in this demo. In particular, the manufacturer had locked down the firmware, so he swapped out the production hardware for the exact same system. But effectively, I mean, what does this mean? We've gotten to a point where systems that, I don't know, when I was playing Doom and the like, I had to buy a pretty expensive computer. Now they're so cheap, so common, so powerful, throwaway devices contain the kind of capability. And again, I'm going to come back to, I doubt John Carmack thought about running Doom on any of these systems when he was designing it. And so, at the end, absolutely. I'd love to have questions. But people have run Doom on all sorts of different things. On cars and phones and ATM machines. I've not actually seen a dishwasher, but that would be a really good one. They don't usually have UIs very well, but I could see it. And a preposterous number of other cases. In some cases, people actually ran Doom inside of another video game. Like they made a Minecraft emulator of a CPU and then ran Doom on it. And the core idea here is people are curious. If we can, we will. Why do we climb mountains? I don't know, because we can. Why do we run Doom on other things? At least for human purposes, part of it is we can. But the question really, I think, is why can we? What is happening in the world where it makes sense that we can run these kinds of things in this way? And additionally, I personally think the approach and the mentality that you bring to breaking a system looks very similar to this approach of running a piece of software on a piece of hardware it was never intended to. And so fundamentally, I look at this and I think curious folks look at these systems and they asked what they could do, not what they should do. And if you ever want to put yourself in that headspace, I think a really great way, I've got kids, young kids, and my kids have routinely thought, what could markers do? Not what should markers do. Walls and faces and all sorts of stuff. If it's possible, they're going to do it. And that is fundamentally the same mindset that these attackers bring to bear. And so, but wait, Luke, that's just a computer. Well, maybe, or maybe that is a computer that does tractor things. And I mean, I think the reason that we're here today is we know that software is eating the world, electronics is eating the world, everything is software defined, and everything in some sense is a computer that does. Cars are just computers that roll. I work for Rolls-Royce. We have a really amazing test bed facility that's basically a computer that controls the testing of our engines. Buildings are computers that control humans and products, and so on and so forth. And most of these, or all of these now really, are systems of systems. Even inside of our cell phones, there's whole systems. You can have lateral movement inside your own cell phone. Pretty wild. So I really like to think of this as could versus should, and it really helps when I go and I talk to the rest of the engineering organization when I describe it this way. What I say is there's kind of this world. If you think about all the states a system could take, There's some set of those that defines what the system could do. And then there's some set of those that we want is what we would desire the system to do. And the attacker exploits the gap, the area between those two circles. And while that's useful, we got to take it a step further. And in the preview that you guys had posted about Carnegie Mellon and Scilab, they talked about how these are hard problems. And then they said they're hard software engineering problems. But then what did they go on and say? They're hard economic problems. They're hard problems of policy, hard problems of decision. Those are all human and socio-technical, not purely technical. So while that's true, it kind of misses the mark, because our mental model of engineering tends to be, we kind of get stuck in what we see and what we know. And so our mental model is really built on engineering, on building physical systems. And for predominantly physical systems, the realities of physics and cost constrain what we can build. Who here has heard and been promised at some point we're going to have flying cars? I mean, I can't even remember how long we've been talking about that. Does anybody have a flying car? I don't. That's a bummer. That'd be really convenient. And why is that? It's because in the real world, it's pretty hard to make it do multiple things in the physical space. We don't typically build cars that could fly equally well. I did watch a Netflix documentary, and they talked about this, but I don't see it normally, where you create a manufacturing environment that during the day it's manufacturing, and in the evening you turn it into a restaurant. And we don't make tech like toothbrushes that could equally well serve as a wrench, because the physical properties of the thing we're working with just don't work that way. But what's the physics of complex electronic hardware? It's something different. And so I think when we think about digital systems, that intuition that we have about the physical world just doesn't work the same. So unlike where physics and cost constrain complexity, in the digital space we get a whole different set of problems. And in particular, designing and producing a microprocessor is wildly expensive. So instead of building exactly what we want, what do? We build something extraordinarily complicated that can do all sorts of things, and then we try to constrain it, to limit what it could do to serve our purposes. So we start with all sorts of could, and we try to limit it down to what it should. So sometimes I like to describe it this way. Imagine a microprocessor is born, and it grows up and has a wonderful youth, and it goes off and it becomes, in our case, a jet engine. But that microprocessor could have been any number of things. It could have been a car. It could have been, I don't know, an internet-connected toothbrush, which I'm not exactly sure why we need, but we nonetheless have. It could be a server in a data center serving up Facebook and the like to you. It could have been all these things. And critically, all that latent possibility, all of that could, is still there. If this is our mental model, it's a little bit wrong for complex electronic hardware, because I think it probably looks more like this. I see a lot of nods. I like that. That's good. We're getting there. But let me put a finer point on it, because this is useful, but this is the problem. Same specification, same functionality. These two systems perform the same functions. Does anybody have the feel? The feel of like a little goosebumpy of like, ooh, I don't want it to do all that stuff, but it can. And most of our design processes are focused around the positive capabilities of the system, specifying what it must do, the system shall. And so we don't really have the right mental models and framework to constrain over here as much and as frequently as we'd like. So while these two things are the same from a functional perspective, they are absolutely not from a risk and resilience perspective. So if we're going to solve this, I think our mentality, our mindset, how we think about these problems is critical. And so that's what I'm going to talk about the rest of this presentation. Now, this idea is really, I'm rephrasing this in my terms of a talk that Thomas Dulien gave at a 2018 presentation for NATO, SciCon. And it's deeply insightful. If you haven't seen it, you should go watch it, because the way he went about this is really delightful and very deeply insightful. And in there he articulated, among a few other ideas, the idea of the anomaly of what he calls the anomaly of cheap complexity, which is what I've just described to you, but he does it in a different approach. And basically what it is that it's easier today to take something wildly complicated or complex and try to make it act like it's simple. And that is really what we do when we do engineering for complex electronic systems, electronics and software. And that's problematic. And that's why I assert, why do we have Doom running on tractors? Because people are curious. Why do we have Doom running on pregnancy tests? Because of the anomaly of cheap complexity and the intersection of that with human curiosity. And so if that's the case, and if this is the world we live in, and I think it is, and I think it's increasingly that, what do we do? Everything we've ever engineered started up here with the way we think. And so I'm going to talk to you about some of the mental models I think we have that sometimes lead us astray. I'm going to talk about three things. One, I think for complex electronic hardware, which means electronics and software, so connected, reconfigurable, and complex electronics, I think we need a new mental model, what it looks like to do engineering. And then I'm going to describe how I think that can help us get out of this cycle of complexity that we've gotten into. Is it going to get us out everywhere? No, but it can get us out in many cases. And when we do, it's delightful. Oh, magnifique. And then finally, I'm going to talk about how secure by design in my mind starts with design. And fundamentally, a lot of this comes down to how do we say no? And you can't fix anything until you see it. And if you go and you look at the thinking on systems thinking and mental models, one of the things they often say is that when your mental model is misaligned with reality, you're consistently surprised. Isn't that just a perfect description of cybersecurity today? Consistently surprised. I don't want to be consistently surprised anymore. I'm sick of it. I would like to feel confident. I would like to feel like we can trust our systems. I want every one of your families to get on an aircraft and fly and know that they are safe and secure. And that means we need something different. So, I want you to all imagine that you were going to go talk to an aspiring engineer, and you were going to describe engineering to them. How would you describe it? I think most of us have what I would describe as an additive view of what engineering is. It's that we start with nothing or nearly nothing, and then we do a bunch of work to build over time whatever it is. Maybe it looks like Legos in your head. I like to think of it like a 3D printer, because I think that's really, deep down, that's what we think about as engineering. But there's a problem with that, because in that view, which I think is valid for mechanical engineering and a bunch of other engineering disciplines, when they're building in the physical world, the problem with that is the assumption that is often uninspected underneath that is that The only functionality this system could exhibit is the stuff we put in it. Our agency is what created the capability. But that's not the reality of a complex world where we have cheap complexity. There, we need something different. And I think it's a constraining mindset, where we take something that could be many things, and we incrementally, our engineering work is about putting those constraints and holding them in place. And so I thought a lot about what's the right mental model for this. And I'm not sure it's quite right, but I think sandcastles are maybe the right answer. Because when you go out on the beach, the sand is all there. It could be anything. You just have to form it into the right thing. But if you ever build a sandcastle, what's the next thing that happens? Somebody else breaks it. They walk up and they kick it. Right? And probably it's somebody that you didn't think was part of your system. Or, if you're lucky enough somebody doesn't do that, entropy destroys it over time. And when we think about software, we think of it as it never changes, it's immutable. Yeah, the bits don't change, but the environment around it does all the time. And there's that permeable relationship and connection of all the other things in and around it that means that there's a half-life even to this immutable software thing. And so if somebody could change one of those constraints we put in place, or the constraints become inadequate in the future, the system could be reshaped into something else. And so there's all that possibility, all that we could come back and reinstate at a later point. And that is where I think we get a lot of our problems. And when we think about what we do here, but we're really living here, we have a tendency to ignore all that. So if we do change that mindset and that mental model, it'd be really nice if we got out of this, what I think is this cycle of self-reinforcing complexity. And so I'm going to use an image to try to explain. Imagine you are in Times Square. There's a bunch of people around. You're hanging out. And if you're walking this way, and then suddenly you see a few people run that way. What happens? Your heart starts to flutter just a little bit. You're like, why are they running? What is happening? A few moments more, a few other people start running. And before long, what's it look like? Looks like chaos. Everybody's chasing. I don't even know what we're chasing. But if everybody else is running that way, we should too. I think that's what we often end up in security. So let's come back to the could versus should and use that to explore this. So if this is our system, how might we change the design? Well, if we think about this as a plane, we got could going left to right and should going north and south. There's at least 4 quadrants where we could move the design. Quadrant 4 over here, that's just a bad idea. Don't do that, right? If the bad part is the area between leftover and the orange, this is a bad design. This up here, this is what we almost always do, right? And what's this cycle, this reinforcing cycle? Oh my gosh, darn it, I found out we have a problem. Look at this complex thing, and it's creating all these issues. I know the answer. Let's add more complex stuff. Guess what we have tomorrow? Now I have 2 complex problems, and 3 and 4 and on and on. And to clarify, I'm not saying we shouldn't do this. I'm saying I don't want us to do it without thinking, because that's where we often end up. Okay, so what are the other options? Well, we got quadrant 2 here, which looks delightful. I like that. But that's expensive, really expensive, right? This is new methods, new tools, new approaches. This is probably what a lot of you guys are thinking about right now. I love it. Great. In practice, This is hard at the coalface, because this stuff is new and novel, it's uncertain. And while I love to do it, it's not an option for me all the time. And then we got quadrant 1. And what's the problem here? It's not a technical problem. This is a business problem. Anybody here bought a system that did less than the last version you bought? No. Because we're prioritizing capability, quadrant 3. And the story here is, when I'm talking about my phone, I probably do want quadrant 3. But if I'm talking about a safety critical system, 1 looks pretty good. And the big problem here is that we often fall into 3 without thinking about 1 and 2. Now, I happen to work for a company that makes safety critical systems, where if things go wrong, the consequences are dire. So we think about these all the time. We already have some of the infrastructure, but not everybody else does. And in particular, if you never see it, you can't fix it. And if your mindset is additive, you're probably not even going to look for options that make your system better by removing. Now, this is basically just a rephrasing of something that safety does already. In the safety engineering world, there's this idea of the safety design order of precedent, which basically says remove things that could cause problems before you go add things to control them. And in the systems security engineering standard from NIST, they've adopted this idea. They've called it the security design order precedent, right over here. This idea is there. The problem is most of your engineers aren't applying it because their mindset around what they do, what value they add, is about adding, and that's not quite right. So if we have tried to stay out of 3 wherever possible, and let me just be really honest, I don't win this very often, but when I do, the life cycle value of 1 and 2, quadrants 1 and 2, is massive, massive. All right, last idea. I started this by asking who here has an internet-connected device in their home and in their bathroom. And then I asked you, does it even matter what the software is? Imagine I have 2 devices, an internet-connected toothbrush and an internet-connected camera. And imagine they have identical electronics. Maybe even identical software, in as much as you got to have the right drivers and software to handle the camera, right? Does it really matter? Some of you are smirking. So the answer is probably not. At least not the first thing that you think about isn't the software. It's about what does it do? What does it do? So why do I feel so differently about these? Because what they are capable of doing in the real world. Not because the software and electronics alone. Just to clarify, and I'm not saying software and electronics don't matter, but I'm saying we should start and make sure we don't lose track of the option for these high-value decisions about making sure we know and are thoughtful about what the system can do. And in particular, if you think about those quadrant 1 and quadrant 2 kind of ideas, those aren't usually technical trade-off decisions. They're socio-technical. They're what is the customer willing to buy? How do we sell it? What priority do we put on things? How do we value things? And those are not things that most of your software and electronics folks are thinking about as much as they could, because that's not their job. Their job is to think about how to implement those things. But you do almost certainly, in a lot of organizations, have people who do think about this. And we need to make sure we involve them and move these decisions there. So these are some, not all, some of the kinds of decisions, the trade-offs that we need to make to be able to move into quadrant 1 and 2. Again, not all the time. It's not possible to do it all the time. But when we can, this is what helps us. I don't know about your organizations, but in my organization, I already have people who think about this. People who are already thinking about the intersection of technology, economics, and society. And so we talk about shift left, but I would argue I think we need to shift all left all the way to systems engineering, because those folks are already thinking about this. There's a whole bunch of activity that's happening, especially in aerospace and defense right now, about how do we engage and how do we bring security into the systems engineering domain. And I'm not saying that software and electronics aren't important. I love you guys. I need you. But if we miss these high-value moments, we're going to end up producing, we're going to fall into quadrant 3, where we're chasing technical solutions, more complexity with more complexity with more complexity, where when we could have gone for simplicity. So, if we start with the assumption, going backwards, I want to make sure we're making the right socio-technical trade-off discussions. We need to engage systems engineering with that. To enable that, we need to give them frameworks and thinking that allows them to see where less is more. And the secure design order precedent, I think, helps with that. Certainly not the only tool, but one. And underneath all of that, especially what I've seen in practice, is if the mindset isn't quite right, it creates challenges because we tend to gloss over and miss things that we should have seen. And I think a core part of this is engineers I think we have a tendency to think our job is to solve technical problems. But I don't think that's right. And I think if you really inspect it, most of you probably disagree too. What I think engineers' job is to solve human problems, and technology is part of it. And sometimes that means we need to add, and sometimes it means we need to take away. Different outcomes begin with different thinking. Maybe start with that constraining mindset. And that's all I've got. Thank you. Any questions? Yes, I promised I'd come back to you. Sorry.
Yeah, would this model also apply for software-only systems?
So I think the answer is yes, because fundamentally both software and cyber-physical systems, I think, have this same problem of the anomaly of cheap complexity. If anything, I think pure software systems, you've got it, it's worse. There's a whole body of work. For instance, the Idaho National Laboratories they've got this idea of the consequence-driven cyber-informed engineering, which is some of the same ideas. How could we use physics to constrain the behavior of the system? That's possible for a cyber-physical system, a lot harder in a purely software system. But the same ideas hold true, and especially the mindset piece, I think, is critical. When I go and I teach inside our organization and I use this analogy, the software people are the ones who are always like, oh, I never even thought about that, because they've spent their whole lives building digital palaces in their minds. I'm a reformed software engineer, I think I can say this. We build all this complex, beautiful logic in our minds, and we kind of have this uninspected assumption that pretty much every good software engineer has ever had, which is, oh my gosh, I could build anything. But isn't that exactly that constraining problem? So yes, I think so. Yeah. Any other questions? Well, if not, thank you.